Abstractions and Codification in Software Engineering, a lecture by Mary Shaw. This is part two. Hi, I'm Chris Tanis. I'm a KMP developer. Tech Support said they're coming out Tuesday. They really promised this time. We'll see. I want to continue with part two of this lecture by Mary Shaw, who is recommended by Grady Booch as his number one person to talks about software engineering and software architectures. And I'm just watching along and reviewing and commenting and ranting, of course, on this what she says. So let's continue on part two.
We hope up.
Okay, she was talking about spiraling, like the engineering practices, like you get better, more you encompass more things. Other engineering practices come in and you're supposed to spiral up. But my point was like a lot of these things die. A lot of these companies go out of business. A lot of the things that a lot of the software that we thought was holy scripture is abandoned, and nobody looks at it. Nobody cares about it. It's been thrown away and it's on a CD someplace. Nobody looks at it. Nobody touches it, and it's forgotten. That's most software.
Let me take a whirlwind tour of the history of software development. I don't want to dwell on this. There's a familiar distinction between so-called programming in the small and programming in the large, and I want to reach back into the depths of the past and extract a previous stage that I'll call programming any which way. In programming any which way, we use mnemonics. Later on, we said specifications are better. In programming any which way, the emphasis was on small programs that just did something.
Right. We were just trying to figure out what the machines could do back then. We weren't really thinking about, and most of the people are tinkerers, so it was roll your own, figure it out all along the way, all the way up until mid 2000s, like 2005, 2003. That started becoming more look it up online, see what else other people are doing. Open source, the whole open source thing became kind of realistic. But before that, you had to figure it out on your own. There were some books, some samples, some other people's source codes you could step through and look at. Some people wrote books. A lot of it was garbage. A lot of it was crap. A lot of it was vanity work. A lot of it was just, what is all this stuff? That's where we learned the spaghetti code, because most people program BASIC starting as one of the first languages. At least that's what I did. There was lots of people did that. And you look at these programs, they're jumping around and making no sense. Like you type them in and they don't work, and you have to figure out why they don't work. So that whole process was building craftsmen that would, you're not only you're writing the code, you're trying to read somebody else's code, see how they put it in there. They didn't even think about that, or they had something in mind. You see all these different techniques. You have to infer them because they're not talking to you. You just, here's the source code, here's a little blurb they say about it, which is probably not even written by them. Anyway, that's what you had to deal with. So there was this training period that a lot of early developers had to go through with that stuff. And we took it for granted. That's just how you do it. It's like, no, now you ask the AI to do it. Yeah, so and also the storage requirements, the storage sizes on these machines these machines were millions of dollars, right? So they thought that having the mnemonics be small, that would make everything else small. Everyone was writing their own stuff, so they're not writing it to be read, they're writing it for the machine to work on it, so they would understand it. They weren't really thinking about having other people extend it or modify it or change it. So that's all this stuff's come later when we have these $1 million, big companies that are like trying to update the software. It's like, well, we weren't taught how to do that. We weren't taught how to make it extendable, updatable, readable, understandable. We were just trying to get the thing to work.
And I marked the shift to actually about 1967, when Don Knuth wrote a textbook that said, gee, folks, you can think about algorithms and data structures as entities in their own right in isolation from the programs that happen to embed them.
Yes, there's lots of little ideas that will probably run if you're trying to make stuff on computers, or you're more than likely to have to either roll your own. That's probably not going to be very efficient, but then there's people that go, I'm going to figure that out, right? And then you come up with the results of their work. Someone went through and did it. It wasn't just plop, here they are. It was like continuously people tinkerers, getting obsessed, just like, this is all I'm doing for the next 6 months as they try and mess with this stuff, or in their spare time or whatever. There's like, nobody's paying them. It's like, can we improve this? Like, somebody just came up with it, figured it out, and they gave it away out of the goodness of their heart, really. We just thinking, oh, now it's an engineering practice. Like, man, it was just a guy that was obsessed and maybe got some encouragement by somebody to keep going. And then when he came up with it, someone encouraged him to share it. Or he thought he would do it on his own to show off.
As Fran said, you got to get the question right. That's a case of getting the question right. At about the same time, Bob Floyd said, you can think in logic, in mathematics, about what your program actually computes. Now, it turns out that it's pretty hard to do that, but knowing that you can, if you care enough, changes the way you think about programs. So a couple of events like that moved us from programming any which.
I think certain sets you can do that with, but not all programs. Come on. Yes, the machine's running on logic, but it's our psychological definition to be perceived by other people with these symbols that we've decided in this structure in this way that both of us have decided on this shared hallucination that provides value that they're willing to pay for. This is not this
way to programming in the small, where we think about input-output specifications rather than just mnemonic identifiers. We think about algorithms and data structures and data types in isolation from programs. And we think about
Wouldn't it be nice if it was just that? Wouldn't it be nice if it was just that?
That execute once.
It's not. It's all this other social per people. What do you want? How do you want it? Who's it for? Why? Context, religion, language, history. Who's the freaking owner of this? Do we really have to do it for the customer? Or are we doing it for this guy?
And terminate, and that's how we reason about them.
Who's paying for this?
In 1975 and 76, Dreamer and Krohn called out the fact that this doesn't solve the whole problem, that there are big systems out there.
Oh, it doesn't solve the whole problem. So somebody was advertising this was going to solve the whole problem. And somebody's like, oh, it solves the whole problem? In 1982, they solved the whole problem, guys. Oh, then it turns out they didn't. Oh, well, I thought the whole problem solved.
And indeed,
I thought we had the whole problem solved by now. Maybe we're not going to solve the whole problem ever. Maybe there's going to have to be people in the loop the whole time.
Had been big systems for 20 years previous to that, where the real issue is how you hold the whole thing together, not the algorithms and data structures that lie inside. So the shift.
Well, that's one problem, right? I think we can figure out how to hold it together, but how to update it, change it, modify it, understand it, debug it, monitor it, let it fail gracefully without crashing everything, or not needing to wake people up at 3 a.m. because the server's down.
Shift from programming in the small to programming in the large was in the mid-70s, and that takes us up to systems with complex specifications, where the problem is really the system structure and the management, long-lived databases, and assemblies of programs that execute continually. You know,
that's our reality. That's our future. We still haven't figured the problems with these systems, how to fix them. They were just like, nope, people will just have to live with pain.
Pre- and post conditions for air traffic control are not a whole lot of interest to me. I don't care about the value the air traffic control system has when it stops. I care a lot about the states that it goes through while it's busy not stopping, though. Okay, what I'd like to do is focus on this abstraction thread. What is it that moves us across that chart? When abstraction is a simplified description or specification of a system that emphasizes some details and suppresses others, and a good abstraction is one that emphasizes the right details. Here's a list of some of the abstractions that we've used through time. I get a free example here because Fran Allen this morning showed how compilers have developed through this, from simply building a compiler as a major accomplishment to having some of the right questions, to having some theories and some technologies that go behind it.
Right. I just want to remind, it's not the compiler who's making these decisions. It's someone who's writing the compiler in these environments, trying to figure out how we can optimize and make these things easier for people. It's not these things just all of a sudden appear. No, it's people pushing these things. And a lot of it doesn't get pushed. A lot of it's trade secrets. A lot of it says stuff we don't share. A lot of it's a ways to put things together that's worth billions of dollars. So you might even promote information that doesn't get you there. Like, all you need is data structures and algorithms, and all your problems are solved. It's like, no. It's this whole other methodology. It's having a culture of these tinkerers that talk around each other, that are supported and are put up with while they fail.
And a lot of that was getting the right abstractions.
While they run experiments that don't work out like they thought. And you gotta rush it. Is that ticket done? You got 2 weeks.
And I'd like to pick up just a couple of these that I've been involved in.
I wonder, it's like, we're not very productive. It's like, you gotta show 2 weeks. It's like, okay, punch the ticket. It's like, yeah, and while you're trying something new, how long is it going to take? We don't know. How long do you want? How much time we got? We can make a stab at it. We can go run at it in a certain way. We can make a run at it a certain way, but you got to let go of some stuff and get real cool with some things real fast.
Get in more detail. So first,
it's not going to look perfect at first, and we're going to try and find. We're going to try and find the customers for this problem. At the same time as we're trying to build this thing, we better have a problem defined and a customer in mind before we even start. Unless we're just doing tinkering around, that's fine. But if you're trying to actually get paid and people to pay you, you better have a problem that you've discovered that you can solve in a better way than they have right now. Cheaper, faster, runner. And it's going to be a while before you actually can get it out to people and get it proven. And so, or you can find methods of trying to get it validated before you even start, which is even more important, actually, to like not go off half-cocked and have a technology without a customer. Have a technique to do something like, bike shedding. Like, okay, that's not what we're trying to build a building here. We're not trying to build a bike shed. Bike shedding, yes, we're going to have a shed for bikes. That's fine. We have this other thing we're trying to work on. Like, why do people want to come to this building?
Useful abstractions for algorithms and data structures happened in the late 1960s. Algorithms and data structures, as I said, were not originally created independently, but rather recreated separately for each program. And to the extent that there was commonality, it was because of this folkloric sharing pulled in dark corners.
Right. There's a certain way. You're going to have a list, so you're going to have a for loop, right? You're going to loop over the list, right? Then you go loop over a list of lists. And you might have a memory thing that has cells of memory that do reference to other things. You might have this is all hand rolled. Now, eventually they got put into the compilers because everyone was doing it the same way with assembly. And there was some commonality, and people talked about it. They how to solve these problems. So they took those little problems, they rolled them up into a compiler language. This is how they were all built. It's individual people, individual efforts, tinkerers.
In 1967, Knuth showed us how to get the right abstractions. Floyd showed us the possibility of formal reasoning.
Did he?
Theories that went beyond this and pulled all the parts together emerged in the
formal reasoning. That's what we got. So we figured the problems.
50s and 1970s. And I think it's fair to say that routine practice in software development now actually relies on these theories. Well, that wasn't, of course, the full solution. And so...
Oh, it wasn't the full solution again. The full solution was promised and not delivered. Maybe we're just never going to get the full solution. Maybe the full solution involves actual engineers figuring out the problem and putting their brain power behind it, where it's worthwhile, where they can still make a living and pay for their house and car and their kids in college and all go on vacation twice a year. Come on now.
He began outgrowing algorithms and data structures even before the theories were solid. In the late 1960s, yeah,
we had to.
Good programmers certainly shared an issue.
The theories come after. I know people are like, oh, these academic people, they really want it to come first. They really want the theory and then the solution to fall out of the theory. It's like, no. No, that's not how it works. I know we want it to work that way, but that's not how it works. There's all very much tinkering around, goofing around with stuff, and then we'll come up with a theory. Maybe, if we're successful, of all the myriad of things that people tried that went nowhere, we have no recognition of like, hey man, that stuff is valuable. You have to have a community of people doing that. You have to have people trying weird stuff out in weird ways and different that hasn't been done that way. Without that community, you're not going to have the stuff that appears every once in a while. It's almost random, man. Some people just get it. Some people, there seems to be they can't reproduce it. That's like a one-shot thing. They're at the right place, right time, right people with the right thing. And then, boop, it was probably going to come out anyway. But that's the guy that brought it forward. I mean, a lot of the stuff is like, you look at it, it's like, yeah, of course, this isn't super clever, but there's other things like, oh, okay, this is kind of clever, like quicksort. Okay, it's like, that's a higher level of reasoning. But like bubble sort, I mean, that's how they do it for a while. Is bubble sort, like, okay.
Intuition that if you get the data structure right, the rest of the program gets much simpler. But there are some problems with taking algorithms and data structures in isolation for this purpose. Conventional language didn't really support data structures ideas very well. There were a series of...
Well, okay, conventional language is this they were just trying to solve another problem. They weren't thinking about pointers and dereferencing. There wasn't that thing. That's what C came along after people started doing that in their assembly language programs. They would be doing all that stuff. C was like, we're gonna make that into something called a pointer. It's like, a what? A pointer? You mean a dereference of a memory address? We're just gonna call that a pointer. It's like this thing points to that. This address points to that address. Ooh, it's a pointer. Ooh. People make such a big deal about that, but that's all it was. It was just codifying and making the C language support that idiom that people were doing already.
Of things that you can point at that identified some of the shortcomings and started providing solutions. In the early 1970s, Bill Wolf and I wrote a paper about the limitations of global variables. At about the same time, Dave Parnas and the
limitations of global variables. It's got some limitations, does it?
Out at NRL doing a specification of a real avionics system.
This is so low level, but at the time it was groundbreaking because people were literally like writing these assembly language programs without any subroutines and just like jumping to different code and jumping back. It was nuts, man. So yeah, these things, even though that we take them for granted for now, at the time they were like breakthroughs because the complexity lowered. And it's like these techniques, and there's this little thing after little thing after thing, and living through it was excruciating, because you would be trying to work on this thing, and you'd be bottlenecked by the sorting, and you're trying to write your own sorting algorithm, and it's like all you can come up with like an index sorter. That's the best you can come up with until you like, oh yeah, there's a whole book of these things, and you go, oh really? And then you be okay, that's when it applies, and then you might have a twist on it, and it might you're moving up. Because you've gone through a gate of this, and you've applied to somebody else's skill set, which for a long time it just wasn't around. It was like when a quick start became, it went through wildfire. People like use it like crazy. I don't know why that keeps hopping up.
Point of view toward information hiding. In 1972, Tony Hoare showed us how to formalize the relationship between an implementation and the abstraction that you would like to have for it, which enabled some new things about abstract data types.
You mean like an interface? Okay. This is just ways of arranging information. This isn't like a breakthrough technology like the transistor, from like going from tube to transistor. This isn't really a technique. It's like a technique. It's a way of arranging things. I don't know if it's a technology. I hate that. And technology is like a thing you build a base, like it's hardware. I think technology is hardware, not some library or the React technology. Are you using React technology? It's like, I don't. That's like kind of overshadowing. It's just a library of it's techniques. Like, keep going.
Just a few years later, Barbara Liskov and Steve Zillis showed how to attach a real piece of mathematics to that specification.
Okay, whatever.
So that set us up for the next step, which is abstract data types. A lot of the software...
This stuff was happening already. You make it seem like there was this incredible scientific breakthrough. It's just like a way of arranging things. But at the time, it was such a breakthrough because people were trying to... These master programs are just like stuck. They can't move forward. They're all using global variables for everything. It's like there's no subroutines. There's no hidden information. Everything's open to everything else. And everyone's like, well, I'll just go get it from there. It's like, no, you have to go through here, and then here, then here, then here, then here, then you can get it. It's like, well, it's just sitting right there. Can I just get it? It's like, no one's stopping you.
Software and programming language research in the 1970s was directed at what is it?
Oh, that doesn't cause a cascading series of problems.
Specification externally. And it turns out you have to go beyond the simple observation and do some things to the programming languages and make them actually support the idea. I've listed a half a dozen things that had to be changed in programming languages in order to support the notion, think about the data structures, create a definition of a type. You think of that now pretty much as an object that hides the representation, that preserves the representation and defends it from all comers, and integrate those things as first-class data types in the language.
More of a class, but
and so the abstract data type research of the 1970s was really directed at addressing some of the particular problems that it takes to make that basic idea real. My work there was with Wolf and London in a language called Alphard.
Alphard? You named a language called Fard? Okay, lady. We know you're... Okay, keep going.
There were 2 or 3 other languages of contemporary period that were working on much the same problem. The one that's probably most familiar to you is Clue, which is Liskov's language. So in the late 1970s...
That's super popular, right? The Clue language, because it was Liskov. Okay, whatever. Wait. No, I mean, the idea of interface is super useful. Yes, to have an API that you can plug in different implementations, like a plug. Ooh, like a plug. Ooh.
We had a good theory for abstract data types. We understood how to build language support for it. It started being taught to undergraduates in the late 1970s and the early 1980s, and by the late 1980s, it had folded together with another thread coming out of Smalltalk.
So they teach the syntax, right? But they don't teach how these things are all put together, because you kind of have to, like, a lot of this stuff is like how you think about problems. And then you have the Alan Kay influence, which everyone ignored because it was too slow at the time. And C++ came along and they took a lot of those ideas and used the same name for the same but different definition, which is just C. It was like a C with classes, I guess. It's like a collaboration. Just put any the popular new thing, just slap it on the language. Half implemented, half baked. People use it, don't use it. Some people say, you've used that, you're out of the club. Like, but it's part of the language, I don't care.
To create object-oriented design that is now the carrier of many of the principles and results from abstract data types. Okay, so far so good, and that takes us once around that cycle. We've gone to models and theories, and now we can start working on new problems and finding ad hoc solutions to them.
Yeah.
We started outgrowing abstract data types.
It's all ad hoc, by the way.
see, 1970s and 1980s, we got to where object.
If we had engineering practices for this, we'd make a tool around it, wrap it, and then we'd have the same problem again. It's all ad hoc.
The design incorporates many of the
can't get away from it. People like the lasers, like, you know, I want to make an engineering practice. We're gonna solve all these problems. Oh, no, all the problems aren't solved. Oh, look, another level of problems that just appeared. That we just subsumed that level problem down one level. We just gotta get away from like we're gonna solve all the problems. Like no, we're not gonna solve all the problems.
But it turns out that abstract data types aren't the best fit for all problems. So what do we do about that?
All problems.
The
obsession.
place we look is in the ad hoc solutions that programmers.
Because there's so many that there's this dream that is possible, right? That we could logically put all the problems that we have as human beings and put them on these machines. That is the dream. The homunculus, the artificial man who does all the bidding for us.
Are using to put their systems together. Programmers now typically write about 6 column inches called the architecture of my system that pulls together the design ideas they have. They have informal descriptions that go with those drawings, and I'd like to show you just a few of those informal descriptions.
Oh, here's where UML got started.
This one's on its side, but it looks just as good on its side.
This is where the UML.
They have boxes and lines, and the lines connect the boxes.
Well, boxes and lines connect the boxes, exactly. And Booch was sitting in the audience and goes, I can make $1 billion with this. I can become an IBM fellow. It's just boxes and lines. I talk about this in my course, How to Program from the Ground Up. There's design, architecture design, software design. Boxes, lines. Boxes within boxes, connected with lines. And Booch was like, we can make this a profession. We could generate source code from those boxes.
I'm not going to talk about these. I just want to remind you that you've seen these pictures at one time or another. Sometimes they have different shapes for the boxes. They rarely have different shapes for the lines. Sometimes they don't even have lines at all.
Yeah.
What they're doing here is trying to describe the architecture for a software system.
Correct.
They use prose that goes along with it. And
right, it's all defined by the team. You just can't look at the diagram. The diagram is for discussion. The diagram is for discussion purposes only. It will not describe the software. It will not describe the system. Everyone talks about these boxes and lines and different. It's very context specific. It's very domain specific. It's very team specific. It's very me and you talking about it specific. You're never going to have a profession or a diagram or a symbology that's going to cover all bases for all time. It's just not going to happen. Stop asking.
The green highlighted phrases here are prose that describe patterns that people recognize. So let's go on to the next slide. Now we're in the 1990s, and I think the interesting ideas have to do with what's really going on when people draw those pictures and write those phrases.
We're trying to communicate ideas for problems that we're trying to solve with a team of people that are going to help me solve the problem. What do these lines and boxes possibly mean? What could this possibly mean? Is there a universal architecture we can solve all problems with? We can find it. I think maybe we could sell that to IBM.
Programmers have a rich set of canonical organizations for systems. Each of the advocates believes that this organization is the one and true path to good system design.
Yes, for them. Who else are you talking about, dude? This is all ad hoc. This is all... Where do you think this stuff comes from? Well, they all believe that they have a universal pipeline architecture. Yeah, for the kinds of problems that they like to solve, the kinds of stuff that they've been working on for the last 20 years, doing thousands of experiments, and they're the ones that made it through the what's it called? The ramparts. They made it up the ramparts. They made it past the boulders coming on them. They made it past the people like, you're stupid. That's a dumb idea. And the late nights alone trying to figure it out. My goddamn quick sort's too slow. You know, all that stuff. Yeah. You better believe they're going to have some set of ideas how to get their problem solved. Come on, man.
It turns out they're not right.
They're not right. Really. They're the ones writing the software, providing solutions to their customers, and they're writing the diagrams. You're taking the diagrams, and you're going, their diagrams aren't right. Oh, interesting, lady.
Sometimes one fits and sometimes another fits.
Yeah, because it totally depends on what they're fucking doing and what they're talking about. You're thinking that they can code what's in the trillions of billions of cells of all the people they know, all that history of all the experiments and all the things they've been doing. You're saying that we putting this diagram of these lines and boxes and the names and the labels of the boxes isn't the whole thing? Really? It's not the whole thing. It's not all of it? Really?
The box and line diagrams are commonly used to describe system organizations, but they are completely informal. They are completely...
Absolutely, and they always will, Booch. They will always See, this is what Bush was like, oh my God, all you gotta do is make a common meaning that we all agree on completely. It's like, what are you talking about, man? Okay, for a one narrow slice of problems, you might be able to do that for, but not in general. Didn't you learn from the flowchart people? You're not gonna be able to do that. You can have it all diagrammed out. And guess what happens tomorrow? It changes. We put this thing into production as is, and all of a sudden there's all kinds of errors, and our product's coming out screwy. And we're late. We're losing customers.
Idiosyncratic. If you look at a bunch of them, you'll see that you can abstract away some patterns, but they don't have common precise meanings.
No shit, it never will, ladies. So stop trying.
A new research area called software architectures is developing to try to make all of this precise, to get it organized and build new models of theory.
This is where the booch comes in. This is where the booch. Enter stage left, the booch with his UML. We are gonna standardize what the meaning of the box and line is. Oh, is that what you're gonna do? You're gonna standardize it, make sure everyone's on the same page.
With samples of the interesting ideas there. The architecture of a software system defines the system in terms of the components in the system and the interactions among the components. It's not just the structure. It also shows how the requirements.
Really, it's not just the structure that defines. It's actually the processes going on inside each one of these boxes, what they mean, and how they work, and what the inputs and outputs. It's not just the lines. This ladies. All right, I'm being harsh on it. Let's keep going.
And it addresses system-level properties like all the IDIs. We need architectural models and definitions that clarify the structural properties that can be composed with each other, and we particularly need a vocabulary of useful abstractions.
And that is domain specific. You're never going to have a general abstracted. And we need an abstracted class structure, an integrated interface hierarchy. And they want a general thing for all engineering, for all time, for all problems, and all implementations. So this is what they were trying to do back then, because the problems were so intractable that the dream was to have all possible solution sets in some codified in some sort of methodology. And they figured that this UML diagram was going to do it. It's like, no, man. Yes, we're all using boxes and lines to describe all kinds of things and processes. And it's not just computer science people. Everybody does it, ding dong. Like any business process is going to have these things. Before computers were electronic and they had human computers, they had these diagrams. You could see the room layouts of where they would have the people doing certain things, doing accounting, we're doing the calculating, we're doing updating, blah, blah,
blah. The next slide shows categorization of some of the patterns that people
factories, same thing.
Know and love. And what I'm going to do is just pick up 3 of these and show you the pictures and kind of put a gloss on the pictures and show what kinds of constructs are involved in the discussion.
All right.
Familiar to everyone who's ever been near Unix is the pipe and filter model. Unix itself will allow you to build that feedback loop, but the shells won't allow you to describe it. It's possible but pretty aggravating to build something like that. And what you'll notice here is that there's a kind of software component called a filter and a kind of relation between the components. So
you're talking about Unix syntax programs that are just applied to Unix that you're trying to do as general software engineering? I don't think people they even used it that way. They did their own thing. That was like for doing batches of stuff. It's not for, I don't think it's for general programming. And you have to use TCP/IP and web APIs. That's what we had to do. So she was trying to do it with the plain old Unix. It's like, I don't know if you're going to get very far.
Which is a data flow relation based on ASCII streams. And that's a pattern that turns out to be useful when you can segment the problem into first step, second step, third step, and pass the data through the steps.
Yeah.
The next slide is another common popular organization.
Like engineering. Splitting things up into steps. Yep. That's kind of what we do. Yep.
Object-oriented organization. Here you practice the principles of information hiding. This organization is useful when the components in the system are hiding a particular representation and telling you how that interacts with the outside world, where each of those is not just a bucket of procedures and data, but has a larger responsibility to preserve the integrity of the abstraction that it is alleged to support.
The hell does that mean? What does that even mean? Let's see if she
they interact via procedure calls, no matter what the object-oriented rhetoric is.
Okay, yes, you have function calls. Yes, people call functions across boundaries that can be inside the same machine or another machine. Okay, what was all that? That's gish gallop.
Third example is a little less familiar. This is a Blackboard system from artificial intelligence. It's used.
Oh, artificial intelligence! They had AI back in '94. I forgot. They were pushing all that crap back then. It was
in a variety of situations that involve, for example, signal processing with noisy data. And here,
okay, the signal processing is different than AI.
Here, There is a central data store that is very complex, and individual independent computations that have no retained state that share the responsibility of doing computations. The magic thing about a blackboard is that the order of execution is spontaneous and opportunistic, and it depends on the state of the data within the blackboard. So there are...
Huh? What's she talking about? Like, you can only communicate to this data thing through an API? What was all that? Did I miss something? It was like gish out like crazy.
3 examples out of that earlier classification of kinds of systems that people actually use. Now, what we're doing currently is trying to develop language and notation, particularly graphical notation, for describing those. This is the next language.
The booch. This is where the booch comes in.
Language problem that Fran Allen asked for. We're addressing the question of how you describe the configurations of systems, not just what goes on inside the components.
Okay, we have the lines and diagrams. So we formal description, because they're gonna go. So the guys that you're selling this to, they're gonna want to go from that formal description right to source code, and you're gonna tell them, yes, we can bypass the programmers. Really? Nah, didn't work.
What I'd like to do is skip ahead to the slide called Important Ideas. There is a language problem behind that in identifying the different kinds of components and the different kinds of relations that they have. I think one of the major problems with reuse currently is that people aren't aware that different compilation units may be organized to be used in different ways. So in Unix you have a filter that provides sort, and you have a system call that provides sort, and they have the same functionality, but they're not even remotely interchangeable.
Oh my God. Are you serious, lady? So she's like trying to make a universal symbol. So if you have the word sort, it always does the same thing on every system in the same way. I mean, standard libraries became a thing, but C had that back then. So what is she saying? The semantic meaning of sort has to be the same, or use the same file structure? Like, what are you talking about, lady?
So the important ideas to carry away are that there are some common patterns for system structure. I showed you 3 pure type forms, but people mix and match and do blends. That you build.
Yeah, it's called knowledge work. That's what we're doing. We're not repeatedly building the same bridge. I know, it's like shocking. People want this to be the way. We're creating something new. So yeah, we can't be defined into some strict structure. And make sure every person that I come across this when I want to communicate my ideas understands the same structure. That's just, you're living in a fantasy land, lady.
By repeated decomposition. I showed you several pictures. Each of those boxes you could open up.
Everybody has different definitions for words. I know, this is like a shocker to people. I know, and especially autists like me and her, we have a real hard time with this. We think that if the definition of the word, everyone has the same definition, and it means the same thing, and that's not true. Everyone has different definitions for the same word. All humans have different definitions of the same word. Even if we grew up together and went to the same thing in the same house and lived and grew up 18 years, that other person who had been through all the same thing that I've been, my brother, my sister, whatever, gonna have a different definition for the same word.
Up and decompose in some way, perhaps a different way, so they may be heterogeneous.
So this is a fool's errand.
System patterns are not tied.
It's really interesting that she hasn't studied philosophy enough to know that everyone has the same. Everyone has different definitions. No one has the same definition for the same word ever in the history of mankind. We've always been discussing. It's a way of trying to approach an idea, trying to explain yourself. And explain ideas and explain to each other, and it's always rough. It's always vague. It's always takes time. Not only you have to speak it, you have to like sketch it, show it, demonstrate it, and then maybe we might be able to communicate what's going on, lady.
To particular applications, you'll hear a lot of discussion about domain-specific software architectures and
Yes, they're all domain-specific. Yes. Any problem we have is going to be very domain. Any problem that we're solving is going to be very domain specific. Yes, to the domain of what the customer is willing to pay for.
Domains tend to be carved up as markets, but you can
find cases. Markets. Yes, that's what I don't know where you get the idea these things just exist in space, free formed. These are machines, are tools for humans to use, and not just program and run programs on. For other people to pay you to solve their problem. Their problem, not your problem. Your problem is to find a problem that you can solve for them. That's your problem. That's my problem. How can I find a problem that I can solve for them? But you're solving the problem for them. They pay you. I know this is shocking.
This is where there's a kind of a problem that appears in market after market after market. And if you carve up your domain solely as markets, then you lose the opportunity to get knowledge about how to solve the problem of the same structure that happens.
But who are you talking about not carving up markets for money? Who are you talking about, lady? Who's doing this out of the goodness of their heart? I mean, we do have those, but it's very rare. They also got people paying for it. They're not just freeform. Somewhere, somehow, someone got paid. Whether he's doing it out of his own money, he's retired, independently, wealthy, whatever, and just feels like doing this for as a lark. But someone paid someone somewhere to do these things. There's a free, cut up the meat in the markets. I think what she's talking about is a standardized library like SQL or MySQL or whatever. Maybe that's what she's referring to. But no, like, where do you think these things come from? Where do you think a tinkerer is just like gets picked up and tried to put into a commercial process because he's found a way to solve a problem using this stuff that people are willing to pay for? Holy shit, if the market comes first, the primary, you have to have somebody paying for you to do the thing, lady. Come on.
To appear in a different market. There's also research activity to be done in understanding how you make the selection of an architecture that fits your problem. I gave you a few hints when I...
You find that ad hoc. There's no research. This is people, I can't believe this got funded. There's no research that's going to generally solve all problems. It's just not going to happen, okay? We're going to have humans involved in the loop.
When I gave you the examples, but that is not even vaguely out of the full course stage yet. Here's a short list of...
It won't be. It didn't go anywhere. It ended. As well it should. It's a dumb idea to try to solve all problems without before you know what the problem is. Not in the middle of it, trying to figure it out. This detail here's this color, this button, this API call over here. Got to take this thing out of here. Could do this over cheaper. This API over here is cheaper. Or we don't even deliver it. You got some new device. What are you talking about, lady? That's all sales driven. What the hell?
Areas that I'm trying to work in. There are some things that you describe as science, describing systems precisely, that involve classifying the idioms, finding taxonomies for them, developing notations. And
taxonomy. See, that's where the inheritance shit went crazy. They were like, oh, I do like taxonomy of the problem space. It's like, no, dude. No, that's like the last part of it.
Tools. There's some things that I'll call engineering that have to do with improving the quality of the design decisions that we make, providing better advice to designers, selecting structures for components.
Designer is the guy that figured out the problem that's being underserved, underutilized, and a profitable way to solve it. Information to the designer, to the decision matrix. It's like
supporting pre-existing software.
People just don't want to get their hands dirty. They want to, I'm a designer, I only design things, so give me the design and I will design it for you to design. It's like, no, you got to get in the mix. You got to talk to the customer. You got to be in there. How are they doing it now? What sucks? How can we make it better? Do you even care about them? Give a shit? And even it has to be something profitable that makes sense. And hopefully something moral, not something to scam. I want to scam them. I'm going to use the AI to scam old people.
And so forth. And then there's education.
Perfect use for it.
What I expect to get out of all this by way of benefits. Let me try to explain it in terms of the software lifecycle. Now, by putting up this waterfall chart, I don't intend to subscribe to the waterfall model. It just turns...
No shit, nobody does. Not even the guy that came up with it. Royce was like, no, man, this is the bad way to do it. This is the way you want to do it. It's the way we can do it in manufacturing, but this is not how we're doing it. He never proposed that. Whoever said the waterfall method, Royce was like proposing that, is like, oh man, Royce, next time, put that shit on the front page. Say, not waterfall. There's not waterfall. You have to do the cyclical thing. There is no waterfall. Not, this is waterfall, page 2. Don't do that.
Turns out to be an easy way to describe where I think the benefits are. First, at the stage of actually describing the architecture, back up there at the level of the design. I guess I should credit Barry Bain with this. Let's see, that's the base for an overlay. Hold on to that. I should credit Barry Bain for this picture. He's the one who put architecture in there between requirements and design.
Oh my God. See, this whole thing about needing to get, this is just obvious shit. You get the requirements, so you got to figure out what we're doing. Then we're going to build something as a methodology of how to do with the architecture. How are we going to put these things together? How's it going to, people going to check their order? Design it? Yes, we're going to, the UI, how all these things are all together, which libraries we're going to use? Yes. Coding it? Yeah, we're going to have to put all this stuff together, test it, put it together. Yes. And then maintenance. Maintenance is, okay, where is the box that says make it understandable, extendable, configurable, maintainable? Nope, just architecture design, straight through. This is waterfall, yo, hello.
Some of the benefit will be in clarifying your intentions about the architecture and making the decisions and implications explicit and supporting system-level analysis in advance of getting down there and running out the algorithms and data structures. But I think there's also the potential for enormous payoff at the later stage in maintenance. Remember the maintenance morass, in which half of the effort is going into simply figuring out what's there.
Yeah. I wonder why. I wonder where the problem was. Because it wasn't put in the budget, man. The budget was not to make it extendable, maintainable, understandable. The budget was, we need to get this out before we go out of business. We got 3 months. We got 3 months, and we have a runway of 3 months. So we either get something out in someone's hands, we start getting traction, or our funders are going to pull out. So what do we do now?
If we can preserve the design intentions into maintenance, I think we stand a chance of reducing the cost of figuring out what's there.
You're lucky if you get the maintenance.
Okay, so if I have to pick a theme for what it is that I do, it's to find the patterns and to find ways to develop abstractions appropriate to the problem.
Right. You're trying to generalize everything. But there's certain classes of things, the domain, the specific problem and the specific solution. You ain't never going to generalize that. It's not possible. That's what they need us for. That's what we do.
But on a practical basis, think about it this way. Here is Edward Bear coming downstairs now, bump, bump, bump on the back of his head. It is, as far as he knows, the only way of coming downstairs. Yeah. But sometimes he feels that there really is another way.
Yeah.
If only he could stop bumping for a moment and think of it.
Yeah. I mean, but when people are given, you have a schedule every time. Were you given the time to implement the sort, past bubble sort? No. You just need to get the accounting system updated so it does 5% instead of 3%. You have to go through the assembly language and figure it out where the guy put it. And now how do I fix it? And how do I test to make sure it's there? Not I'm replacing quicksort. And how long is that going to take? I don't know. I don't know how long it's going to take. It'll take as long as if the many ideas I can have running at this thing, and I might not get it. So maybe we can have somebody else help out or work on it at the same time. And we could bounce ideas together. No, just one guy is only allowed to do it. And you only got 2 weeks. And if you can't do it, well, then forget it. Well, what do you think the whole thing's been like that? Bump, bump, bump down the stairs.
And then he feels that perhaps there isn't.
Yeah. Because the financial system, the businesses are not set up for this. Because most of the time, those efforts fail. When you're trying to do something new and trying to change something, you got to have that tinkerer mindset where you're doing it over long periods of time. And you're itching it out, and you have a spurt here and there where you get a big results. You're getting close, and all of a sudden, all this education don't work. How long is it going to take? I don't know. When it's like, how long are you going to give me? I'm going to try my best. And I can't be called a bad person if I don't get it when I didn't know if it was even possible to get there in the first place. And that's why it's going to be tinkerers and people doing it on their own time. Well, a lot of this stuff is where it's going to come from because these companies just like, where's the profit going to happen? I need it now. You're a good business. I really appreciate her bringing some of this stuff. She's at least trying, right? She's at least trying. Kind of needs a little bit better philosophy about what humans are capable of doing and what the problem space, how big it is for humans and how varied it is and how you're not going to be able to generalize it. But I like your presentation. Let's listen to some Q&A. Come
on. Okay, I can ask for questions. I will entertain questions.
The advanced systems which are built now are a result of collaboration of several engineering disciplines. An advanced airplane, for example, military airplane, it has several types of engineers cooperating to get to the product. What do you think, if software is at a craft stage or a commercial stage, what do you think is the prospect of integrating with all these engineering disciplines which have had more time to develop? I've seen, for example, Annie Nerode advocating that computer science is not good on its own. You have to sort of change the education system so that you have control engineers and computer science at the same time. What do you think?
Maybe. Yeah, I can see that.
I think we could do a much better job of infusing appreciation for an engineering approach into the undergraduate program as a whole.
Yeah, I mean, good luck, though.
So I think there's a lot of improvement to be made in...
I mean, the thing about the computer science stuff is like, yeah, you got to know the coding part, but that's like maybe 20%. It's like, how do you talk to people with these ideas? How do you communicate your ideas? How do you structure things to be readable, maintain? How do you convince people that's a good idea to do, to spend time on? To get correct, or like realize that, hey, we're gonna do like a few versions of this thing, and it might take a while before we get the thing that we want. Like having the understanding of the business people who are picking around the checks, like, you know, the first one's not gonna be it. But it's gonna get you. We're gonna get you there. It's like, no, the first one must be completed at all costs, and we're gonna spend all of our time and budget on that one. It's like, no, No, that's probably a good way to fail, right? Like, I don't know. People don't know that. This is an iterative process. They only see the end results. They don't see the thousands of iterations it takes to get this stuff correct.
In computer science. So yeah, improve computer science education. Continue to press for the maturity of software engineering as a discipline, because that will help. I think there's also some things to do on the other side.
I don't know how that's going to help. How is it making a discipline help? What does that mean? We have to convince the business people to allow us to have some discipline in there, but they don't want to pay for it, man. They don't want to pay for it, so that doesn't happen. So we cut the corners, and you get the products you have right now.
I didn't bring the slide that talks about the major myths of software that need to be abused, but there's a list of myths about software. One is software is soft and changes are easy.
No, definitely not. It's not designed for that. It's for designing, creating it, for writing it. It's easy, but modifying it at scale. No, we still haven't solved it. With Chris from the future, Mary Shaw, we haven't solved that one, and no one seems to be giving a shit about it. It seems to just get worse and worse and worse. They're saying the AI is going to solve it for us, but I've yet to see that. They've been claiming it for several years now, and they still haven't demonstrated it. So, still an ongoing problem.
Software engineering is
not going to be solved. Management. It's going to be solved in a different way. It's going to be solved from philosophy. It's going to be solved by philosophy. It's like not trying to use every buzzword for your resume to get your next job in 2 years. That can't be part of it.
A software system is just a big program.
I mean, that is what it is. It is a big program. But how do you break it down? Where are the boundaries? It depends on your problem space, right? So it's all this it depends stuff. And the thing is, loves trade secrets. Trade secrets.
And all you need is a smart domain expert who needs a little basic.
That's the hope. So that's what the managers, the business people really want it to be. They want to go back to the factory, which Harvard told them, right? Every business is just a factory. Widgets in, money in, widgets out, money out. Not what widget are we making for who, how, why. Nope, just widgets.
I think the ability of software engineers to work with the engineers of the other systems in which they're building would be enhanced by a little motion on both sides. On our part to improve the maturity of software engineering and the degree to which it's infused in the undergraduate education, and on their side to stop kidding themselves about what software is and isn't.
Okay, fair enough. Agreed.
To advance up to that level and to get into the right professional societies and that kind of thing?
The question is that if, as software engineering moves up into the third tier, into engineering, is it going to be harder for women because it's going to be harder to get into the right groups and clubs and actually do the work and so forth? Well, the content is solid technical content, and I don't think anybody here should be...
It's just that, look, here's the real thing. Girls aren't tinkerers. I know it's shocking. Most girls are not tinkerers. They don't want to mess with this stuff. They don't want to deal with it. They want to twiddle with something on their own in the middle of the dark. It's very few people. I've had some women bosses and things like that, and they're the exception. But for the most part, they want a good job. They want a nice job, but they don't want to do all the things that you have to do to really get this thing going. It seems like they're just not interested. And there was a very small percentage like to want to go through all the bullshit. Dude, these platforms and these APIs and the way these coding, these languages work and how they're presented, the IDEs, incredibly intensely overcomplicated for what we're actually trying to do. And all of them are different. They're all trying to do the same damn thing. They're all copied from each other. They don't tell you that. And it's like, no, we got a new thing. It's an amazing new thing. It's our thing. It's a weird win fit. It's like, yeah, but you just copied theirs, and it's like 2% better, and it's like 5 times more cost. It's like all this crap. So this is the thing. It's like you really got to be into it. And a lot of women they aren't into it, man. And to expect them to be that level, the level of dedication, is it's not just going into a job and then putting it away at the end. Like this knowledge work crap, as you know, as a developer, dude, it's constant. It doesn't go away. You can't just put it away and come back in and start over again. I'm waiting for simple problems, but for if you're really going for it, dude, adventure-driven stuff, or actually trying to do software engineering and applying real problems and stuff like that, it's like you're obsessed with this shit. It's constant. And if a thing doesn't work, you want to know why. Like most women just don't want to dick with it, dude. So it's not a problem as for access. It's like, because we ran that experiment recently. Yeah, it's not the access. It's just not will. It's just a different mindset. Most women just really aren't interested, like way guys are. We're all truly nerding out, goofy about. Oh, the new API came out. Oh my god, I'm all over it. And we're like, oh, another thing to fucking learn. And it was like, oh my god, this solves a thing where I can now apply this other thing. It's like, no, damn, I gotta learn a new API. It's like that's the attitude. It's like, oh, okay, to keep this job, to keep this position, have a modicum of looking like I'm capable of doing these things, I gotta keep up. It's like, okay.
Should be any more alarmed at the technical content in software engineering than the technical content that they're already coping with in calculus or introductory engineering or
true, but it's not that. It's not the same thing. It's more than that. It's more like Legos. Like, yes, you have to learn all the Lego pieces do, but then you have to put them all together in a unique way that's just yours. That's crafty. It's very craft-like. It's very tinkery, because that's where the shit fucking comes from.
I don't personally perceive strong barriers to the professional societies. The professional societies have not segmented into different societies for the real engineers and the management people and everything else. The primary professional societies for most of us are the ACM and the IEEE, and they cover the whole spectrum. So I don't see that there are any societal barriers that will be added.
Those two societies have fallen down. Fallen down. They're elitists. They're very, I don't know. They're not really pulling their weight. It's for computer science, at least. They've allowed these boot camps to show up and take a lot of their time. Like, there should be an ACM boot camp. And there should be a IEEE boot camp that actually gets people at the tinkerer phase as kids involved. Not, well, to join our club, you got to be the blah 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 blah. Oh yeah, that's gonna get kids really involved with it. That's gonna get new tinkers at the bottom of the pile coming up, doing all their experiments, being encouraged, falling down, fail.
At that point because they're the same societies.
All right, that's cool. Anyway, thanks for listening to me rant, and I guess that's the end of this series. And I'll be on to the next one. Give me a like and subscribe, and go give Computer History Museum a like and subscribe, and I'll talk to you soon.